Page is yours.
Yep. So my name is Peder Sparell, and I work with a cybersecurity company in Sweden, Linguistic Consulting. And I've done some work on linguistic cracking of passphrases using Markov chains. Originally, this was master's thesis work with my boss, Michael Simowitz, as supervisor. But he couldn't be here today, so I will be doing all the talking. So we'll start with some background. We often hear recommendation or requirements saying our passwords should be long and complex. In order to remember very long passwords, it's basically necessary to skip the complex part and just and based on phrases. And constantly increasing requirements on length of passwords leads to increased use of these simpler passphrases. And available cracking methods of today are not very efficient when there's more than 2 words included. And languages are relatively predictable and far from random, which we should utilize. So if we try to crack only linguistically correct phrases, could we find an effective way to crack long passwords? And how should we generate these phrases? And finally, is it advisable to recommend users to use a passphrase as a password? This work was a test of concept, and we have delimited the passphrases to this definition. It consists of a longer password, which is composed of 2 or more words, mostly 3 or more, without white space. And we only look at lowercase passphrases in this work, the maximum length of 20 characters. So a Markov chain, or a Markov process, is a process where transitions to other states are determined by probability distribution based on only the current state. The sequence of state transitions in the process builds up a Markov chain. But in the Markov chain of order M, the states are redefined a bit to be able to include a kind of a history of M number of states. And one way to do language modeling is to build up phrases from n-grams together with Markov chains of order n-1. And n-grams are sequences with n number of elements, which could be either characters or words. An n-gram of order 3 is often called a trigram, of order 4, a 4-gram, and so on. And the static, excuse me, the that was hard. The statistics for the probability distribution of the n-grams are generated from counting number of occurrences of n-grams in larger texts. And from that it can later be examined which character is more likely to follow a certain sequence of other characters. So a little bit about our implementation of the Markov process. Our implementation consists of an application generating as linguistically correct phrases as possible, and either saved into a file, which can then be used as a word list in any cracking application, or send the phrases directly to a cracking application which supports input streams from standard in. If the files are saved, you can reuse the list for future cracking as long as there is space on your hard drive. Kind of a time memory trade-off. So the actual phrase generation is split into 2 phases, with 1 console application for each. First application will take a large text source as large text file as input, extract the n-grams, and generate n-gram statistics. The result of that is saved into a new text file where a number of occurrences are shown of each n-gram. The application in the next phase will use these n-gram statistics, and by going through a Markov process, it will generate the phrases that will be our output. In phase one, the application is started from the console, and the user specifies the text file that should be analyzed, as well as the desired order and level of the n-grams. The level could be word level or character level. The source file is read and processed line by line, reading out and counting the n-grams. Some filtering and changes are made. For example, all punctuation marks are replaced by a single dot to represent sentence breaks. Including the sentence breaks makes it possible to select the start of the generated phrases by taking into account which n-grams are more common in the start of sentences. And we can also do the same in the end of the phrases to end them in a more sensible way. So in character mode, we also still keep track of white space, which is used in the process as word breaks, even if the final output is stripped of white space. So when the file is read to the end, our n-gram statistics are saved to a text file, which will be used in the next phase. Starting the actual phrase generation in phase two, you can set both a lower and upper limit on the length of the generated phrases you want. And you can also choose if you want to have a certain number of words in your phrases. And of course, you choose the n-gram file to use. The program reads the n-gram statistics file and sorts the n-grams in a list of states of size n-1, where every state has sublists of the possible next character or word, depending on mode, sorted by the number of occurrences in the source text. The example shows a small extract from a list of 4-gram statistics, where the states on the left consist of 3 characters, and the sublists to the right are sorted according to the number of occurrences in the source text. So the starting states, which begin with a dot, are loaded into a separate list, which is also sorted according to the number of occurrences. And you can also choose to set a threshold value. The n-grams that don't have a higher occurrence than this value will be ignored. So there will be no generated phrases containing those n-grams. For each starting state, phrases are then built up one at a time using a recursive function that goes through all possibilities in order according to these n-gram statistics. So now I will try to describe what our goal is and which values we need to calculate to determine if we have achieved that goal. So there are different estimates of the complexity or entropy of the English language. Some estimates are based on human guesses, where you already know about earlier letters, so you have a perfect model of the language. NIST has adopted their interpretation of entropy slightly towards the passwords context. So we will be using their interpretation of entropy as our target. They assign different values to different characters in the text, where the first is assigned 4 bits of entropy, and for each subsequent character, the assigned entropy is lowered gradually. As an example, for a 16-character phrase, you get an entropy of 30 bits. A password of 16 totally random characters have an entropy of 75 bits, which means it should be 40 trillion times easier to guess a correct English phrase of this length than a randomly chosen. So for the evaluation, we will compare our values against those we get from the NIST way of calculating entropy. And we call this the target entropy. Then for each phrase list we generate, we calculate how large entropy this phrase list potentially could have, only based on how many phrases it contains. We call this the potential history. If the phrase list has a lower potential entropy than the target entropy, it means it probably contains too few phrases, and there are more phrases in the English language than in our phrase list. If it's higher than the target entropy, the number of generated phrases is enough to cover the language, but it doesn't mean they are linguistically correct. So to make an estimate of how correct the phrases in the list are, we calculate the efficiency after a successful cracking attempt by dividing number of cracked hashes by the number of sought hashes. With this efficiency and the total number of phrases in the list, we then calculate an estimated entropy of the phrase file. So for example, if half of the target passwords were cracked, the estimated entropy becomes one step higher than if all were cracked. So finally, some results, or some testing variables. Testing samples were created by some of my colleagues at Linguistic Consulting. I asked them for hashes of 10 passphrases from each one, and I received 66 hashes. They hashed the passwords themselves, so I had no idea what the passphrases were. Only thing I know was how many of each length there was. The n-gram statistics were created from 3 different sources to get some variety on the underlying language and see the effect of that. The one source most used was the one from the news source, since it was the largest with 3 million sentences. And the variables used to generate the phrase list can be derived from the file names chosen in the results later. So if you see a file named like this, it means, well, the L20 means that the length of the phrases are 20 characters long. W6 means there are always 6 words in these phrases. T5 means the threshold is set to 5. N3 means n-gram of order 3 was used, trigrams. W means that the n-grams were at word level, and news means that the source text was the one from the news sites. So here are the results from a few different attempts. If we start by looking at the phrases with length 10 at the top here, it may be interesting to note the difference in number of generated phrases between the character level and word level. The first file cracked 7 out of 15 hashes, which is a pretty good result. But because the potential entropy was so large compared to the target entropy, which is that one, the estimated entropy also became high. Also interesting is that despite the change of the threshold value at word level on line 2 and 3 here, and almost 6 times as many phrases in the file with no threshold, they both cracked the same number of hashes. And that makes the estimated entropy larger for the file containing more phrases, meaning that it was less effective. So at length 14, phrases based on the 5-gram character level was not able to crack any hashes, but when 8 grams were used instead, 2 hashes were cracked. The word level files cracked 2 other hashes, which between them were the same. So the total of unique hashes cracked at phrase 14 was 4. So at length 16, the criteria on the test samples were that the phrases should consist of 4 to 6 words. So the files were restricted to that, and that unfortunately means that the target entropy no longer match exactly, and it's actually slightly lower than 30. Here the files are divided into groups with different number of words per phrase in order to limit the file sizes. So it's the lines with the sums that are most interesting here, the group rows. So group 2 was the best attempt in the terms of estimated entropy, even though the 6-word file ruined the result drastically. We also compared different text sources at the word level of phrases containing 5 words. Those 2. And the hashes that were broken in these 2 files were different or unique, which shows that the choice of source text is clearly influencing. In total, there were 6 unique passphrases cracked of length 16. At the phrase length of 20, phrases started to get extremely long, and none of the first 2 files were able to crack anything. But when we let the phrase generation work for a while, we finally got the results on the 20 character phrases as well. Bottom 2 line shows the successful results. And that the phrase generation took weeks to complete, if you look at that column. The potential entropy is lower than the target entropy, which indicates that despite the longer generation times, there were still too few phrases to cover the English language. So the total number of cracked 20 character phrases were 2. This chart shows the different entropy values from the table in the previous slides to get a better overview. The goal is that the bar for the estimated entropy, the dark blue, to be as low as possible, but not lower than the bar of the target entropy, the light blue. All 3 bars should be as equal as possible. And keep in mind that this is a 2-log scale, so 1 unit corresponds to a doubled increase. You can easily see here what I mentioned in the last slide, that the most effective attempt was the group 2 of the phrase length 16 at word level. And because there is no other publicly available effective cracking attack on this length of passphrases, the phrase list's estimated entropies are here compared to the entropy of brute force attack. Anything is more effective than brute force, of course, but the question is how much. So this is also a 2 logarithmic scale, so 1 bit decrease means double the efficiency. And we can easily see that this works method of cracking, although it can be further developed and optimized, is far more efficient than a brute force attack. And we also did a test against real-life passwords on the LinkedIn leaked hash dump. This was done using only our previously created list with the same phrase lengths. And with some help from password stats from Adeptus Mechanicus. We estimated the number of lowercase password of each length, and our method seems to generally crack about 10% of this target scope. But in that target scope, several passwords are included that still are not linguistically correct phrases, which was the target of our work. So probably this is a little better. So that we succeeded in cracking that many phrases should be seen as a good result of that. And compared to brute force, it's of course superior in terms of entropy. The goal to reach the target entropy was not really achieved, but even so it feels like the Markov model is a pretty effective language model to crack password phrases, especially in lack of other methods. If you look at what type of n-grams was most effective, it was the 3 grams on the word level, despite that the word level phrases took slightly longer to generate. And all things considered, if you use passphrases, they should at least be longer than 20 characters, and all character sets should be used. This work was just a test of concept, and the method and implementation could be improved a lot. For example, performance optimizations of the implementation are possible and desirable, and including other character sets are necessary for use in real situations. Improvements in the algorithm is, like the phrase generation order, is also possible to make it more effective. So if you want more info, throw me a mail or visit our company website. There will soon be English content about this work in the news or the blog section. And the code will also be released as open source on SourceForge soon if you want to get a copy or contribute to code. Thank you.